Welcome back. In this unit of chemistry, we're going to be talking all about the mole. Unfortunately, I'm not talking about this cute little guy right here. I'm talking about the chemistry mole. So what is a mole? A mole is a name for a specific quantity of things. Just like a dozen is 12, a pair is 2, a mole is a specific quantity. And a mole is equal to 602 hexillion, which if we wrote it out, would look like this, which if you're thinking, wow, that's a lot of zeros, you were right. After the 602, that is 21 zeros. That's a lot. Which is why we write it out as 6.02 times 10 to the 23rd, because that's a lot easier to write out. That number is important. You're going to need to memorize that number. You're going to be using that number a lot. So 1 mole is equal to 6.02 times 10 to the 23rd. Something to keep in mind, a mole is not an abbreviation for molecule. Some students think that it is. It is not. A mole is a mole, a molecule is a molecule. The two are not equal to each other. You will also hear a mole called Avogadro's number, because Avogadro is the person we credit it with. So Avogadro's number is also 6.02 times 10 to the 23rd. So how many donuts are in 1 dozen donuts? 12. You go to Dunkin' Donuts, you say you want a dozen, they're giving you 12 donuts. How many donuts are in 1 mole of donuts? Well, we just learned that a mole is 6.02 times 10 to the 23rd, so that means it's 6.02 times 10 to the 23rd donuts. That's a lot of donuts. How about jelly beans? If I ask you to give me 1 dozen jelly beans, how many jelly beans would you give me? You'll give me 12, because a dozen is still 12, whether we're talking about donuts or jelly beans. How many jelly beans are in 1 mole of jelly beans? 6.02 times 10 to the 23rd, because a mole is still a mole, whether we're talking about donuts or jelly beans. So how many of anything are in 1 dozen anything? 12. A dozen always means 12. Similarly, how many of anything are in 1 mole of anything? 6.02 times 10 to the 23rd, because a mole is 6.02 times 10 to the 23rd, no matter what we are talking about. So, as far as the definition for a mole is concerned, it is the number of atoms equal to the number of atoms in exactly 12.0 grams of carbon-12. So that is how we came to the number of the mole, by looking at how many atoms were in 12.0 grams, which is 1 mole, of carbon-12. And that quantity was 6.02 times 10 to the 23rd atoms, which is where we got our number from. So, just to kind of put things in perspective for you, how large do you think 1 mole of jelly beans is? So, 6.02 times 10 to the 23rd jelly beans. It is as big as the Earth. If you had that many jelly beans, it would take up the whole entire Earth. How long do you think a mole of donuts stacked up would be? So 6.02 times 10 to the 23rd donuts, one on top of the other. Just like that. Ready to have your mind blown? That stack would be long enough to go from the Earth to the Sun and back 200 billion times. So the Earth to the Sun, back to the Earth 200 billion times. That is a crazy amount of donuts. So how large do you think a mole of water molecules is? So think about water. Water is H2O. If you look at the periodic table, you can calculate the molar mass of water, H2O. We learned how to do that first semester. H2O right there. And you would get that it is about 18 grams. Okay? How large do you think a mole of sugar molecules is? So let's talk about glucose. C6H12O6. If you do the same thing, go to the periodic table, add it all together, you're going to get 342 grams. So why are the moles of water molecules and sugar molecules so much smaller than the moles of jelly beans and donuts? Because 18 grams and 342 grams aren't really that big at all. And it's because of the size. A water molecule and a sugar molecule are way smaller than a jelly bean or a donut. You can see a jelly bean or a donut with your naked eye, no problem. You can't see a single water molecule. You can't see a single sugar molecule. So since they start off bigger, they are going to end up bigger when we convert it to moles. And that's something important to remember. So why do you think scientists use the mole? We're going to be seeing the practicality of the mole throughout this entire unit. But scientists use the mole because it's a way to put things in a standard size. 1 mole is 6.02 times 10 to the 23rd anything. So it allows us to kind of standardize everything. So I want you to think of the mole as a bridge. It connects the microscopic world, the world of atoms and molecules, the things we cannot see with our naked eyes, to that macroscopic world that we live in, where all the things that you can see with your naked eyes. So it is easier to think about atoms as a group, or a mole, than it is to think about atoms individually, because they can't be seen, and they usually exist in groups. There are very few instances that you just have one atom chilling all by itself. It's usually hanging out with a whole bunch of friends. So the mole is this bridge, and it allows us to connect moles, mass, volume, and particles, which we are going to be doing later in this unit. So what is the desired unit in a lab for mass? When we are using the electronic balance at your lab station, what unit does it give you? Your number in. That's right, the gram. So we need to relate the atomic mass, AMU, atomic mass units, of an element to the amount of the element in grams, since that's our desired unit. And the mole is how we are going to relate these two. The molar mass of a substance is equal in magnitude to the atomic mass of the substance. Now, molar mass should be a little familiar to you because we did this first semester. So, for example, the atomic mass of hydrogen is 1.01 AMU. So you can get that on the periodic table, which means the molar mass of hydrogen is 1.01 grams per mole. So for every mole of hydrogen we have, it would weigh 1.01 grams. So molar mass, we're going to go over this again, but it should be a review. So this should be easy peasy for you. So the mass of 1 mole, or 6.02 times 10 to the 23rd of a substance, is molar mass. It is equal to the magnitude of the atomic mass of the element. So that atomic mass on the periodic table is what that element's molar mass is. If it is in a compound, we're going to have to add and multiply them together. It's measured in grams per mole, which we write out as G/mol. The molar mass of each individual element is listed on the periodic table. Remember, you'll always be given that periodic table, so you don't have to memorize these. So let's do some quick practice. What is the molar mass of sodium? Well, when you look on the periodic table, you should find that it is 22.99 grams per mole. What is the mass of a mole of nitrogen? 14.01 grams. What is the mass of 6.02 times 10 to the 23rd atoms of fluorine? Now think about this for a second. What is 6.02 times 10 to the 23rd equal? Well, it equals a mole. So this question is essentially asking you, what is the mass of a mole of fluorine? Pretty simple. You look on the periodic table and get 19.00 grams. So what do you call the mass of a mole? You call it the molar mass. That's what we were doing here. Once again, some review on calculating molar mass. To calculate molar mass, you add the masses of each atom in a compound together. For example, determine the molar mass of CaCl2. All right. So first off, how many calcium atoms are there in CaCl2? There are just one. How many chlorine atoms are there in CaCl2? There are two. So that means whatever our mass of chlorine is, we have to multiply it by 2 because we have 2 chlorines. So you're going to add the mass of one calcium atom, 40.08, plus the mass of 2 chlorine atoms, 2 times 35.45, and you are going to get 110.98 grams per mole. We always round to 2 decimal places. All right, I want you to pause this video and practice these 3 on your own. Unpause the video and come back to see the answers when you're done. Now remember, I'm not going to show you the work for these, so you need to work these out on your own. Just knowing the answer isn't very helpful to you. All right, what is the molar mass of magnesium nitrate, MgNO3 2? Our correct answer is 148.33 grams per mole. What is the mass of 1 mole of aluminum hydroxide, AlOH3? 78.01 grams. And what is the mass of 6.02 times 10 to the 23rd molecules of water? Knowing that 6.02 times 10 to the 23rd is a mole, and that this question is essentially just asking us what is the mass of a mole of water, we get 18.02 grams. This brings us to our next topic in this, which is percent composition. So you know what a percentage is. What does it mean if you got an 88% on a test? If you got an 88% a test, that would tell you you got 88% of the questions correct. So of the total of questions, you got 88 of them correct, 88% of them. If the test had 100 questions, that would mean you got 88 questions correct. If the test had 50 questions, that would mean you had 44 correct. It is telling you how much of the total you got correct. And that's what a percentage is. It's telling you how much of something out of the total something is. A percentage is simply a part of a whole. Part divided by whole times 100. How would you calculate the percentage of people wearing glasses in your chemistry class? Well, you would take the number of people who had glasses, say 5 people, divided by the total number of people in your class, say it's 25. 5 divided by 25 is 0.2. You multiply that one by 100, and you would say 20% of the people in your class have glasses. So percent composition is another type of percentage. So percent composition is the percentage by mass of each element in a compound. So percent composition equals the mass of an element in a compound divided by the total mass of that compound, so the molar mass, times 100. You're going to round your answer to 2 decimal places, just like we've been doing. The units of percent composition are percent, pretty easy to remember, and the total percent composition of a compound must add up to 100. This is an easy way to check your answer to make sure that you at least have a chance of getting it correct, because if your answer doesn't add up to 100, you 100% know you're wrong. So let's look at some examples together. So you are asked to find the percent composition of carbon in the following: C3H7OH. All right? And CO2. So let's look at how we would have solved both of those. So the mass of carbon is 3, because we have 3, times 12.01 off the periodic table, which equals 36.03 grams per mole. Once again, we're only concerned about carbon. That's all the question asks us about. The total mass of C3H7OH is 60.11 grams per mole. So we're going to take 36.03, divide it by 60.11, and multiply it by 100 to get 59.94% carbon in that molecule. Carbon dioxide is a little bit easier. The question only asks us about carbon. So in carbon dioxide, CO2, we only have one carbon. Mass of one carbon is 12.01 grams per mole. Total mass of CO2 is 44.01 grams per mole. So we're going to take 12.01 grams per mole, divide it by 44.01 grams per mole, multiply by 100 to get 27.29. That is the step-by-step process that you would solve for any element, for any compound out there. You just find out what the mass of the element you're looking for is, the mass of the total, divide the part by the total, multiply by 100, and you get a percentage. Easy peasy. So percent composition in practice. I want you to determine the percent composition for all of the elements in the two compounds that we just did, C3H7OH and CO2. Now remember, you already did carbon, so you don't have to do carbon over again, but I want you to apply the same thing to finding the hydrogen and the oxygen in those two compounds. I also want you to tell me, if you add the percent composition for each element in a compound, what will the answer always be? So pause this video and come back when you are done. All right, so as far as question number 1, C3H7OH, carbon is 59.94%. We already got that one. Hydrogen is 13.44%, and oxygen is 26.62%. Number 2 is actually a little bit easier because you already had carbon, 27.92. So the only other one you need to find was oxygen, which is 72.71. Now, in the case where you only have two elements, number 3 helps you out. So if you add the percent composition for each element of a compound together, what will the answer be? Well, the answer will always be 100. So in number 2, you could have technically taken 100 and subtracted 27.29 from it, because you already worked that out in the previous problem, to just get the 72.71. Now keep in mind that only works when you only have two elements, but it can save you some time. All right, I want you to come to class ready to practice our molar mass and percent composition tomorrow.